Fluorine is a chemical element. It has symbol F and atomic number 9. It is the lightest halogen and exists at standard conditions as a highly toxic, pale yellow diatomic gas. Fluorine is extremely reactive, as it reacts with all other elements except for the light inert gases. Liquid fluorine, F2 at extremely low temperature. Spectral lines of fluorine. Regarding fluorine, 9F, and regarding fluorine, its pronunciation is fluorine, fluorine, or fluorine. Its allotropes are alpha, beta, C. Allotropes of fluorine. Its appearance in gas is very pale yellow, liquid is bright yellow, and solid is alpha is opaque, beta is transparent. Its standard atomic weight AR degree, F, is 18.998403162 plus or minus 0.00000005 or 18.998 plus or minus 0.001, abridged. Regarding fluorine in the periodic table, it is above chlorine, right of oxygen, and left of neon. Its atomic number, Z, is 9. Its group is group 17, halogens. Its period is period 2. Its block is p block. Its electron configuration is helium-2 squared 2p to the 5th. Its electrons per shell is 2, 7. Regarding its physical properties, its phase at STP is gas. Its melting point is F2, 53.48 Kelvin, negative 219.67 degrees Celsius, negative 363.41 degrees Fahrenheit. Its boiling point is F2, 85.03 Kelvin, negative 188.11 degrees Celsius, negative 306.60 degrees Fahrenheit. Its density, at STP, is 1.696 G/L when liquid, at BP, is 1.505 G/cm cubed. Its triple point is 53.48 Kelvin, 0.252 kPa. Its critical point is 144.41 Kelvin, 5.1724 MPa. Its heat of vaporization is 6.51 kJ/mol. Its molar heat capacity is Cp, 31 J/mol K, at 21.1 degrees Celsius, and Cv, 23 J/mol K, at 21.1 degrees Celsius. Its vapor pressure at 38 Kelvin is 1, at 44 Kelvin is 10, at 50 Kelvin is 100, at 58 Kelvin is 1 K, at 69 Kelvin is 10 K, and at 85 Kelvin is 100 K. Regarding its atomic properties, its oxidation states is -1, 0, oxidizes oxygen. Its electronegativity is Pauling scale, 3.98. Its ionization energies are first, 1681 kJ/mol, second, 3374 kJ/mol, third, 6147 kJ/mol, and more. Its covalent radius is 64 picometers. Its van der Waals radius is 135 picometers. Regarding its other properties, its natural occurrence is primordial. Its crystal structure is cubic. Its thermal conductivity is 0.02591 W/mK. Its magnetic ordering is diamagnetic, -1.2 times 10 to the -4th. Its Ca number is 7782-41-4. Regarding its history, its naming is after the mineral fluorite, itself named after Latin fluo, to flow, in smelting. Its discovery was by André-Marie Ampère, 1810. Its first isolation was by Henri Moissac, June 26, 1886. It was named by Humphrey Davy and André-Marie Ampère. Regarding its isotopes of fluorine, here are the abundances and half-lives, T1/2, under main isotopes, and modes, and products under decay. 18F, trace, 109.734 minutes, beta plus, 180. 19F, 100% stable. Among the elements, fluorine ranks 24th in universal abundance and 13th in terrestrial abundance. Fluorite, the primary mineral source of fluorine which gave the element its name, was first described in 1529, as it was added to metal ores to lower their melting points for smelting. The Latin verb fluo meaning flow gave the mineral its name. Proposed as an element in 1810, fluorine proved difficult and dangerous to separate from its compounds, and several early experimenters died or sustained injuries from their attempts. Only in 1886 did French chemist Henri Moissac isolate elemental fluorine using low-temperature electrolysis, a process still employed for modern production. Industrial production of fluorine gas for uranium enrichment, its largest application, began during the Manhattan Project in World War II. Owing to the expense of refining pure fluorine, most commercial applications use fluorine compounds, with about half of mined fluorite used in steel making. The rest of the fluorite is converted into corrosive hydrogen fluoride en route to various organic fluorides, or into cryolite, which plays a key role in aluminium refining. Molecules containing a carbon-fluorine bond often have very high chemical and thermal stability. Their major uses are as refrigerants, electrical insulation, and cookware, and PTFE, Teflon. Pharmaceuticals such as atorvastatin and floxetin contain CF bonds. The fluoride ion from dissolved fluoride salts inhibits dental cavities, and so finds use in toothpaste and water fluoridation. Global fluorochemical sales amount to more than $69 billion a year. Fluorocarbon gases are generally greenhouse gases with global warming potentials 100 to 23,500 times that of carbon dioxide, and SF6 has the highest global warming potential of any known substance. Organofluorine compounds often persist in the environment due to the strength of the carbon-fluorine bond. Fluorine has no known metabolic role in mammals. A few plants and sea sponges synthesize organofluorine poisons, most often monofluorostates, that help deter predation. Fluorine atoms have 9 electrons, 1 fewer than neon, and electron configuration 1s² 2s² 2p to the 5th, 2 electrons in a filled inner shell and 7 in an outer shell requiring 1 more to be filled. The outer electrons are ineffective at nuclear shielding, and experience the high effective nuclear charge of 9 2 = 7, this affects the atom's physical properties. Fluorine's first ionization energy is third highest among all elements, behind helium and neon, which complicates the removal of electrons from neutral fluorine atoms. It also has a high electron affinity, second only to chlorine, and tends to capture an electron to become isoelectronic with the noble gas neon. It has the highest electronegativity of any reactive element. Fluorine atoms have a small covalent radius of around 60 picometers, similar to those of its period neighbors oxygen and neon. Regarding external videos, there is bright flames during fluorine reactions and fluorine reacting with cesium. Fluorine 3D molecule. The bond energy of difluorine is much lower than that of either Cl2 or Br2 and similar to the easily cleaved peroxide bond. This, along with high electronegativity, accounts for fluorine's easy dissociation, high reactivity, and strong bonds to non-fluorine atoms. Conversely, bonds to other atoms are very strong because of fluorine's high electronegativity. Unreactive substances like powdered steel, glass fragments, and asbestos fibers react quickly with cold fluorine gas. Wood and water spontaneously combust under a fluorine jet. Reactions of elemental fluorine with metals require varying conditions. Alkali metals cause explosions and alkaline earth metals display vigorous activity in bulk. To prevent passivation from the formation of metal fluoride layers, most other metals such as aluminium and iron must be powdered, and noble metals require pure fluorine gas at 300 to 450 degrees Celsius, 575 to 850 degrees Fahrenheit. Some solid nonmetals, sulfur, phosphorus, react vigorously in liquid fluorine. Hydrogen sulfide and sulfur dioxide combine readily with fluorine, the latter sometimes explosively. Sulfuric acid exhibits much less activity, requiring elevated temperatures. Hydrogen, like some of the alkali metals, reacts explosively with fluorine. Carbon, as lamp black, reacts at room temperature to yield tetrafluoromethane. Graphite combines with fluorine above 400 degrees Celsius, 750 degrees Fahrenheit, to produce non-stoichiometric carbon monofluoride. Higher temperatures generate gaseous fluorocarbons, sometimes with explosions. Carbon dioxide and carbon monoxide react at or just above room temperature, whereas paraffins and other organic chemicals generate strong reactions. Even completely substituted haloalkanes such as carbon tetrachloride, normally incombustible, may explode. Although nitrogen trifluoride is stable, nitrogen requires an electric discharge at elevated temperatures for reaction with fluorine to occur. Due to the very strong triple bond in elemental nitrogen, ammonia may react explosively. Oxygen does not combine with fluorine under ambient conditions, but can be made to react using electric discharge at low temperatures and pressures. The products tend to disintegrate into their constituent elements when heated. Heavier halogens react readily with fluorine, as does the noble gas radon. Of the other noble gases, only xenon and krypton react, and only under special conditions. Argon does not react with fluorine gas, however, it does form a compound with fluorine, argon fluorohydride. Crystal structure of beta-fluorine. Spheres indicate F2 molecules that may assume any angle. Other molecules are constrained to planes. Animation showing the crystal structure of beta-fluorine. Molecules on the faces of the unit cell have rotations constrained to a plane. At room temperature, fluorine is a gas of diatomic molecules, pale yellow when pure, sometimes described as yellow-green. It has a characteristic halogen-like pungent and biting odor detectable at 20 ppb. Fluorine condenses into a bright yellow liquid at -188 degrees Celsius, -306 degrees Fahrenheit, a transition temperature similar to those of oxygen and nitrogen. Fluorine has two solid forms, alpha and beta fluorine. The latter crystallizes at -220 degrees Celsius, -364 degrees Fahrenheit, and is transparent and soft, with the same disordered cubic structure of freshly crystallized solid oxygen, unlike the orthorhombic systems of other solid halogens. Further cooling to -228 degrees Celsius, -378 degrees Fahrenheit, induces a phase transition into opaque and hard alpha fluorine, which has a monoclinic structure with dense, angled layers of molecules. The transition from beta to alpha fluorine is more exothermic than the condensation of fluorine, and can be violent. Only one isotope of fluorine occurs naturally in abundance, the stable isotope 19F. It has a high magnetogyric ratio and exceptional sensitivity to magnetic fields. Because it is also the only stable isotope, it is used in magnetic resonance imaging. 18 radioisotopes with mass numbers from 13 to 31 have been synthesized, of which 18F is the most stable with a half-life of 109.77 minutes. 18F is a natural trace radioisotope produced by cosmic ray spallation of atmospheric argon as well as by reaction of protons with natural oxygen, 180 plus P to 18F plus N. Other radioisotopes have half-lives less than 70 seconds, most decay in less than half a second. The isotopes 17F and 18F undergo beta plus decay and electron capture, lighter isotopes decay by proton emission, and those heavier than 19F undergo beta minus decay, the heaviest ones with delayed neutron emission. Two metastable isomers of fluorine are known, 18MF, with a half-life of 162.7 nanoseconds, and 26MF, with a half-life of 2.21 milliseconds. Regarding solar system abundances, here are the atomic numbers, elements, and relative amounts. 6. Carbon, 4,800. 7. Nitrogen, 1,500. 8. Oxygen, 8,800. 9. Fluorine, 1. 10. Neon, 1,400. 11. Sodium, 24. 12. Magnesium, 430. Among the lighter elements, fluorine's abundance value of 400 ppb, parts per billion, 24th among elements in the universe, is exceptionally low. Other elements from carbon to magnesium are 20 or more times as common. This is because stellar nucleosynthesis processes bypass fluorine, and any fluorine atoms otherwise created have high nuclear cross-sections, allowing collisions with hydrogen or helium to generate oxygen or neon respectively. Beyond this transient existence, 3 explanations have been proposed for the presence of fluorine. During Type II supernovae, bombardment of neon atoms by neutrinos could transmute them to fluorine. The solar wind of Wolf-Rayet stars could blow fluorine away from any hydrogen or helium atoms, or fluorine is borne out on convection currents arising from fusion in asymptotic giant branch stars. Fluorine is the 13th most common element in Earth's crust at 600 to 700 ppm, parts per million, by mass. Though believed not to occur naturally, elemental fluorine has been shown to be present as an occlusion in antozonite, a variant of fluorite. Most fluorine exists as fluoride-containing minerals. Fluorite, fluorapatite, and cryolite are the most industrially significant. Fluorite, CaF2, also known as fluorspar, abundant worldwide, is the main source of fluoride, and hence fluorine. China and Mexico are the major suppliers. Fluorapatite, Ca5, PO4, 3F, which contains most of the world's fluoride, is an inadvertent source of fluoride as a byproduct of fertilizer production. Cryolite, Na3AlF6, used in the production of aluminium, is the most fluorine-rich mineral. Economically viable natural sources of cryolite have been exhausted, and most is now synthesized commercially. Fluorite, pink globular mass with crystal facets. Fluorapatite, long, prismatic crystal, dull in luster, protruding, at an angle, from matrix of aggregate-like rock. Cryolite, a parallelogram-shaped outline with diatomic molecules arranged in 2 layers. Other minerals such as topaz contain fluorine. Fluorides, unlike other halides, are insoluble and do not occur in commercially favorable concentrations in saline waters. Trace quantities of organofluorines of uncertain origin have been detected in volcanic eruptions and geothermal springs. The existence of gaseous fluorine in crystals, suggested by the smell of crushed antozonite, is contentious. A 2012 study reported the presence of 0.04% F2 by weight in antozonite, attributing these inclusions to radiation from the presence of tiny amounts of uranium. Steel-making illustration from De Re Metallica. In 1529, Georgius Agricola described fluorite as an additive used to lower the melting point of metals during smelting. He penned the Latin word fluors, fluor, flow, for fluorite rocks. The name later evolved into fluorspar, still commonly used, and then fluorite. The composition of fluorite was later determined to be calcium difluoride. Hydrofluoric acid was used in glass etching from 1720 onward. Andreas Sigismund Marggraf first characterized it in 1764 when he heated fluorite with sulfuric acid, and the resulting solution corroded its glass container. Swedish chemist Carl Wilhelm Scheele repeated the experiment in 1771, and named the acidic product fluospatsyrin, fluorspar acid. In 1810, The French physicist André-Marie Ampère suggested that hydrogen and an element analogous to chlorine constituted hydrofluoric acid. He also proposed in a letter to Sir Humphrey Davy dated August 26, 1812 that this then unknown substance may be named fluorine from fluoric acid and the -ine suffix of other halogens. This word, often with modifications, is used in most European languages. However, Greek, Russian, and some others, following Ampère's later suggestion, use the name phytor or derivatives, from the Greek phi thetaero iota omicron, thorios, destructive. (1887) Drawing of Moissan's apparatus. Initial studies on fluorine were so dangerous that several 19th-century experimenters were deemed fluorine martyrs after misfortunes with hydrofluoric acid. Isolation of elemental fluorine was hindered by the extreme corrosiveness of both elemental fluorine itself and hydrogen fluoride, as well as the lack of a simple and suitable electrolyte. Edmund Fremy postulated that electrolysis of pure hydrogen fluoride to generate fluorine was feasible and devised a method to produce anhydrous samples from acidified potassium bifluoride. Instead, he discovered that the resulting, dry, hydrogen fluoride did not conduct electricity. Fremy's former student Henri Moissan persevered, and after much trial and error found that a mixture of potassium bifluoride and dry hydrogen fluoride was a conductor, enabling electrolysis. To prevent rapid corrosion of the platinum in his electrochemical cells, he cooled the reaction to extremely low temperatures in a special bath and forged cells from a more resistant mixture of platinum and iridium, and used fluorite stoppers. In 1886, after 74 years of effort by many chemists, Moissan isolated elemental fluorine. In 1906, 2 months before his death, Moissan received the Nobel Prize in Chemistry, with the following citation: "In recognition of the great services rendered by him in his investigation and isolation of the element fluorine. The whole world has admired the great experimental skill with which you have studied that savage beast among the elements." An ampoule of uranium hexafluoride. The Frigidaire division of General Motors, GM, experimented with chlorofluorocarbon refrigerants in the late 1920s, and Kinetic Chemicals was formed as a joint venture between GM and DuPont in 1930, hoping to market Freon 12, CCl2F2, as one such refrigerant. It replaced earlier and more toxic compounds, increased demand for kitchen refrigerators, and became profitable. By 1949, DuPont had bought out Kinetic and marketed several other Freon compounds. Polytetrafluoroethylene, Teflon, was serendipitously discovered in 1938 by Roy J. Plunkett while working on refrigerants at Kinetic, and its superlative chemical and thermal resistance lent it to accelerated commercialization and mass production by 1941. Large-scale production of elemental fluorine began during World War II. Germany used high-temperature electrolysis to make tons of the planned incendiary chlorine trifluoride, and the Manhattan Project used huge quantities to produce uranium hexafluoride for uranium enrichment. Since UF6 is as corrosive as fluorine, gaseous diffusion plants required special materials, nickel for membranes, fluoropolymers for seals, and liquid fluorocarbons as coolants and lubricants. This burgeoning nuclear industry later drove post-war fluorochemical development. Fluorine has a rich chemistry, encompassing organic and inorganic domains. It combines with metals, nonmetals, metalloids, and most noble gases, and almost exclusively assumes an oxidation state of -1. Fluorine's high electron affinity results in a preference for ionic bonding. When it forms covalent bonds, these are polar, and almost always single. Alkali metals form ionic and highly soluble monofluorides. These have the cubic arrangement of sodium chloride and analogous chlorides. Alkaline earth difluorides possess strong ionic bonds but are insoluble in water, with the exception of beryllium difluoride, which also exhibits some covalent character and has a quartz-like structure. Rare earth elements and many other metals form mostly ionic trifluorides. Covalent bonding first comes to prominence in the tetrafluorides. Those of zirconium, hafnium and several actinides are ionic with high melting points, while those of titanium, vanadium, and niobium are polymeric, melting or decomposing at no more than 350 degrees Celsius, 660 degrees Fahrenheit. Pentafluorides continue this trend with their linear polymers and oligomeric complexes. 13 metal hexafluorides are known, all octahedral, and are mostly volatile solids but for liquid MOF6 and REF6, and gaseous WF6. Rhenium heptafluoride, the only characterized metal heptafluoride, is a low-melting molecular solid with pentagonal bipyramidal molecular geometry. Metal fluorides with more fluorine atoms are particularly reactive. Regarding the structural progression of metal fluorides, sodium fluoride, ionic. Bismuth pentafluoride, polymeric. Rhenium heptafluoride, molecular. Boiling points of hydrogen halides and chalcogenides, showing the unusually high values for hydrogen fluoride and water. Hydrogen and fluorine combine to yield hydrogen fluoride, in which discrete molecules form clusters by hydrogen bonding, resembling water more than hydrogen chloride. It boils at a much higher temperature than heavier hydrogen halides and unlike them is miscible with water. Hydrogen fluoride readily hydrates on contact with water to form aqueous hydrogen fluoride, also known as hydrofluoric acid. Unlike the other hydrohalic acids, which are strong, hydrofluoric acid is a weak acid at low concentrations. However, it can attack glass, something the other acids cannot do. Chlorine trifluoride, whose corrosive potential ignites asbestos, concrete, sand, and other fire retardants. Binary fluorides of metalloids and p-block nonmetals are generally covalent and volatile, with varying reactivities. Period 3 and heavier nonmetals can form hypervalent fluorides. Boron trifluoride is planar and possesses an incomplete octet. It functions as a Lewis acid and combines with Lewis bases like ammonia to form adducts. Carbon tetrafluoride is tetrahedral and inert. Its group analogues, silicon and germanium tetrafluoride, are also tetrahedral but behave as Lewis acids. The pnictogens form trifluorides that increase in reactivity and basicity with higher molecular weight, although nitrogen trifluoride resists hydrolysis and is not basic. The pentafluorides of phosphorus, arsenic, and antimony are more reactive than their respective trifluorides, with antimony pentafluoride the strongest neutral Lewis acid known, only behind gold pentafluoride. Chalcogens have diverse fluorides. Unstable difluorides have been reported for oxygen, the only known compound with oxygen in an oxidation state of +2, sulfur, and selenium. Tetrafluorides and hexafluorides exist for sulfur, selenium, and tellurium. The latter are stabilized by more fluorine atoms and lighter central atoms, so sulfur hexafluoride is especially inert. Chlorine, bromine, and iodine can each form mono, tri, and pentafluorides, but only iodine heptafluoride has been characterized among possible interhalogen heptafluorides. Many of them are powerful sources of fluorine atoms, and industrial applications using chlorine trifluoride require precautions similar to those using fluorine. These xenon tetrafluoride crystals were photographed in 1962. The compound's synthesis, as with xenon hexafluoroplatinate, surprised many chemists. Noble gases, having complete electron shells, defied reaction with other elements until 1962 when Neil Bartlett reported synthesis of xenon hexafluoroplatinate, xenon difluoride, tetrafluoride, hexafluoride, and multiple oxyfluorides have been isolated since then. Among other noble gases, krypton forms a difluoride, and radon and fluorine generate a solid suspected to be radon difluoride. Binary fluorides of lighter noble gases are exceptionally unstable. Argon and hydrogen fluoride combine under extreme conditions to give argon fluorohydride. Helium has no long-lived fluorides, and no neon fluoride has ever been observed. Helium fluorohydride has been detected for milliseconds at high pressures and low temperatures. Immiscible layers of colored water, top, and much denser perfluoroheptane, bottom, in a beaker. A goldfish and crab cannot penetrate the boundary, quarters rest at the bottom. Chemical structure of naphthalene, a fluoropolymer used in fuel cells and many other applications. The carbon-fluorine bond is organic chemistry's strongest, and gives stability to organofluorines. It is almost non-existent in nature, but is used in artificial compounds. Research in this area is usually driven by commercial applications. The compounds involved are diverse and reflect the complexity inherent in organic chemistry. The substitution of hydrogen atoms in an alkane by progressively more fluorine atoms gradually alters several properties. Melting and boiling points are lowered, density increases, solubility in hydrocarbons decreases, and overall stability increases. Perfluorocarbons, in which all hydrogen atoms are substituted, are insoluble in most organic solvents, reacting at ambient conditions only with sodium in liquid ammonia. The term perfluorinated compound is used for what would otherwise be a perfluorocarbon if not for the presence of a functional group, often a carboxylic acid. These compounds share many properties with perfluorocarbons such as stability and hydrophobicity, while the functional group augments their reactivity, enabling them to adhere to surfaces or act as surfactants. Fluorosurfactants, in particular, can lower the surface tension of water more than their hydrocarbon-based analogues. Fluorodolomers, which have some unfluorinated carbon atoms near the functional group, are also regarded as perfluorinated. Polymers exhibit the same stability increases afforded by fluorine substitution. For hydrogen, in discrete molecules, their melting points generally increase too. Polytetrafluoroethylene, PTFE, the simplest fluoropolymer and perfluoroanalog of polyethylene with structural unit CF2, demonstrates this change as expected, but its very high melting point makes it difficult to mold. Various PTFE derivatives are less temperature tolerant but easier to mold. Fluorine at ethylene propylene replaces some fluorine atoms with trifluoromethyl groups. Perfluoroalkylase alkanes do the same with trifluoromethoxy groups, and naphthalene contains perfluoroether side chains capped with sulfonic acid groups. Other fluoropolymers retain some hydrogen atoms. Polyvinylidene fluoride has half the fluorine atoms of PTFE and polyvinyl fluoride has a quarter, but both behave much like perfluorinated polymers. Elemental fluorine and virtually all fluorine compounds are produced from hydrogen fluoride or its aqueous solutions, hydrofluoric acid. Hydrogen fluoride is produced in kilns by the endothermic reaction of fluorite, CaF2, with sulfuric acid. CaF2 plus H2SO4 to 2HF, G, plus CaSO4. The gaseous HF can then be absorbed in water or liquefied. About 20% of manufactured HF is a byproduct of fertilizer production, which produces hexafluorosilicic acid, H2SiF6, which can be degraded to release HF thermally and by hydrolysis. H2SiF6 to 2HF plus SiF4. SiF4 plus 2H2O to 4HF plus SiO2. Industrial fluorine cells at Preston. Moissaw's method is used to produce industrial quantities of fluorine. via the electrolysis of a potassium bifluoride/hydrogen fluoride mixture. Hydrogen ions are reduced at a steel container cathode and fluoride ions are oxidized at a carbon block anode, under 8 to 12 volts, to generate hydrogen and fluorine gas respectively. Temperatures are elevated, Kf2HF melting at 70 degrees Celsius, 158 degrees Fahrenheit, and being electrolyzed at 70 to 130 degrees Celsius, 158 to 266 degrees Fahrenheit. Kf, which acts to provide electrical conductivity, is essential since pure HF cannot be electrolyzed because it is virtually non-conductive. Fluorine can be stored in steel cylinders that have passivated interiors, at temperatures below 200 degrees Celsius, 392 degrees Fahrenheit, otherwise nickel can be used. Regulator valves and pipework are made of nickel, the latter possibly using Monel instead. Frequent passivation, along with a strict exclusion of water and greases, must be undertaken. In the laboratory, glassware may carry fluorine gas under low pressure and anhydrous conditions. Some sources instead recommend nickel Monel PTFE systems. While preparing for a 1986 conference to celebrate the centennial of Wausau's achievement, Carl O. Christ reasoned that chemical fluorine generation should be feasible since some metal fluoride anions have no stable neutral counterparts, their acidification potentially triggers oxidation instead. He devised a method which evolves fluorine at high yield and atmospheric pressure. 2KMnO4 plus 2KF plus 10HF plus 3H2O2 to 2K2MnF6 plus 8H2O plus 3O2 up. 2K2MnF6 plus 4SbF5 to 4KSbF6 plus 2MnF3 plus F2 up. Christ later commented that the reactants had been known for more than 100 years and even Wausau could have come up with this scheme. As late as 2008, some references still asserted that fluorine was too reactive for any chemical isolation. Fluorite mining, which supplies most global fluorine, peaked in 1989 when 5.6 million metric tons of ore were extracted. Chlorofluorocarbon restrictions lowered this to 3.6 million tons in 1994. Production has since been increasing. Around 4.5 million tons of ore and revenue of $550 million were generated in 2003. Later reports estimated 2011 global fluorochemical sales at $15 billion and predicted 2016 to 18 production figures of 3.5 to 5.9 million tons, and revenue of at least $20 billion. Froth flotation separates mined fluorite into two main metallurgical grades of equal proportion. 60 to 85% pure metspar is almost all used in iron smelting, whereas 97% plus pure acid spar is mainly converted to the key industrial intermediate hydrogen fluoride. Clickable diagram of the fluorochemical industry according to mass flows. SF6 current transformers at a Russian railway. At least 17,000 metric tons of fluorine are produced each year. It costs only $5 to $8 per kilogram as uranium or sulfur hexafluoride, but many times more as an element because of handling challenges. Most processes using free fluorine in large amounts employ in situ generation under vertical integration. The largest application of fluorine gas, consuming up to 7,000 metric tons annually, is in the preparation of UF6 for the nuclear fuel cycle. Fluorine is used to fluorinate uranium tetrafluoride, itself formed from uranium dioxide and hydrofluoric acid. Fluorine is monoisotopic, so any mass differences between UF6 molecules are due to the presence of 235U or 238U, enabling uranium enrichment via gaseous diffusion or gas centrifuge. About 6,000 metric tons per year go into producing the inert dielectric SF6 for high-voltage transformers and circuit breakers, eliminating the need for hazardous polychlorinated biphenyls associated with oil-filled devices. Several fluorine compounds are used in electronics, rhenium and tungsten hexafluoride in chemical vapor deposition, tetrafluoromethane in plasma etching and nitrogen trifluoride in cleaning equipment. Fluorine is also used in the synthesis of organic fluorides, but its reactivity often necessitates conversion first to the gentler ClF3, BrF3, or IF5, which together allow calibrated fluorination. Fluorine at pharmaceuticals use sulfur tetrafluoride instead. Aluminium extraction depends critically on cryolite. As with other iron alloys, around 3 kilograms, 6.5 pounds, met spar is added to each metric ton of steel. The fluoride ions lower its melting point and viscosity. Alongside its role as an additive in materials like enamels and welding rod coats, most acid spar is reacted with sulfuric acid to form hydrofluoric acid, which is used in steel pickling, glass etching and alkane cracking. 1/3 of HF goes into synthesizing cryolite and aluminium trifluoride, both fluxes in the Hall-Héroult process for aluminium extraction. Replenishment is necessitated by their occasional reactions with the smelting apparatus. Each metric ton of aluminium requires about 23 kilograms, 51 pounds, of flux. Fluorosilicates consume the second largest portion, with sodium fluorosilicate used in water fluoridation and laundry effluent treatment, and as an intermediate en route to cryolite and silicon tetrafluoride. Other important inorganic fluorides include those of cobalt, nickel, and ammonium. Organofluorides consume over 20% of mine fluorite and over 40% of hydrofluoric acid, with refrigerant gases dominating and fluoropolymers increasing their market share. Surfactants are a minor application but generate over $1 billion in annual revenue. Due to the danger from direct hydrocarbon, fluorine reactions above -150 degrees Celsius, -240 degrees Fahrenheit, industrial fluorocarbon production is indirect, mostly through halogen exchange reactions such as Schwarz fluorination, in which chlorocarbon chlorines are substituted for fluorines by hydrogen fluoride under catalysts. Electrochemical fluorination subjects hydrocarbons to electrolysis in hydrogen fluoride, and the Fowler process treats them with solid fluorine carriers like cobalt trifluoride. Halogenated refrigerants, termed freons in informal contexts, are identified by R numbers that denote the amount of fluorine, chlorine, carbon, and hydrogen present. Chlorofluorocarbons, CFCs, like R11, R12, and R114 once dominated organofluorines, peaking in production in the 1980s. Used for air conditioning systems, propellants, and solvents, their production was below 1/10 of this peak by the early 2000s, after widespread international prohibition. Hydrochlorofluorocarbons, HCFCs, and hydrofluorocarbons, HFCs, were designed as replacements. Their synthesis consumes more than 90% of the fluorine in the organic industry. Important HCFCs include R22, chlorodifluoromethane, and R141B. The main HFC is R134A with a new type of molecule HFO1234YF, a hydrofluorolefin, HFO, coming to prominence owing to its global warming potential of less than 1% that of HFC 134A. Fluorosurfactant-treated fabrics are often hydrophobic. About 180,000 metric tons of fluoropolymers were produced in 2006 and 2007, generating over $3.5 billion revenue per year. The global market was estimated at just under $6 billion in 2011. Fluoropolymers can only be formed by polymerizing free radicals. Polytetrafluoroethylene, PTFE, sometimes called by its DuPont name Teflon, represents 60 to 80% by mass of the world's fluoropolymer production. The largest application is in electrical insulation since PTFE is an excellent dielectric. It is also used in the chemical industry where corrosion resistance is needed, in coating pipes, tubing, and gaskets. Another major use is in PFTE-coated fiberglass cloth for stadium roofs. The major consumer application is for non-stick cookware. Jerked PTFE film becomes expanded PTFE, EPTFE, a fine-pored membrane sometimes referred to by the brand name Gore-Tex and used for rainwear, protective apparel, and filters. EPTFE fibers may be made into seals and dust filters. Other fluoropolymers, including fluorine and ethylene propylene, mimic PTFE's properties and can substitute for it. They are more moldable, but also more costly and have lower thermal stability. Films from two different fluoropolymers replace glass in solar cells. The chemically resistant, but expensive, fluorine ionomers are used as electrochemical cell membranes, of which the first and most prominent example is NAFN. Developed in the 1960s, it was initially deployed as fuel cell material in spacecraft and then replaced mercury-based chloralkali process cells. Recently, the fuel cell application has re-emerged with efforts to install proton exchange membrane fuel cells into automobiles. Fluoroelastomers such as Viton are cross-linked fluoropolymer mixtures mainly used in O-rings. Perfluorobutane, C4F10, is used as a fire extinguishing agent. Fluorosurfactants are small organofluorine molecules used for repelling water and stains. Although expensive, comparable to pharmaceuticals at $200 to $2,000 per kilogram, they yielded over $1 billion in annual revenues by 2006. Scotchgard alone generated over $300 million in 2000. Fluorosurfactants are a minority in the overall surfactant market, most of which is taken up by much cheaper hydrocarbon-based products. Applications in paints are burdened by compounding costs. This use was valued at only $100 million in 2006. About 30% of agrichemicals contain fluorine, most of them herbicides and fungicides with a few crop regulators. Fluorine substitution, usually of a single atom or at most a trifluoromethyl group, is a robust modification with effects analogous to fluorine at pharmaceuticals, increased biological stay time, membrane crossing, and altering of molecular recognition. Trifluorine is a prominent example, with large-scale use in the U.S. as a weed killer, but it is a suspected carcinogen and has been banned in many European countries. Sodium monofluorostate, 1080, is a mammalian poison in which one sodium acetate hydrogen is replaced with fluorine. It disrupts cell metabolism by replacing acetate in the citric acid cycle. First synthesized in the late 19th century, it was recognized as an insecticide in the early 20th century, and was later deployed in its current use. New Zealand, the largest consumer of 1080, uses it to protect kiwis from the invasive Australian common brush-tailed possum. Europe and the US have banned 1080. Topical fluoride treatment in Panama. Population studies from the mid-20th century onwards show topical fluoride reduces dental caries. This was first attributed to the conversion of tooth enamel hydroxyapatite into the more durable fluorapatite, but studies on pre-fluoridated teeth refuted this hypothesis, and current theories involve fluoride aiding enamel growth in small caries. After studies of children in areas where fluoride was naturally present in drinking water, controlled public water supply fluoridation to fight tooth decay began in the 1940s and is now applied to water supplying 6% of the global population, including 2/3 of Americans. Reviews of the scholarly literature in 2000 and 2007 associated water fluoridation with a significant reduction of tooth decay in children. Despite such endorsements and evidence of no adverse effects other than mostly benign dental fluorosis, opposition still exists on ethical and safety grounds. The benefits of fluoridation have lessened, possibly due to other fluoride sources, but are still measurable in low-income groups. Sodium monofluorophosphate and sometimes sodium or tin, 2, fluoride are often found in fluoride toothpastes, first introduced in the U.S. in 1955 and now ubiquitous in developed countries, alongside fluoridated mouthwashes, gels, foams, and varnishes. Floxidin capsules. 20% of modern pharmaceuticals contain fluorine. One of these, the cholesterol reducer atorvastatin, Lipitor, made more revenue than any other drug until it became generic in 2011. The combination asthma prescription Seretide, a top 10 revenue drug in the mid-2000s, contains two active ingredients, one of which, fluticasone, is fluorinate. Many drugs are fluorinate to delay inactivation and lengthen dosage periods because the carbon-fluorine bond is very stable. Fluorination also increases lipophilicity because the bond is more hydrophobic than the carbon-hydrogen bond, and this often helps in cell membrane penetration and hence bioavailability. Tricyclics and other pre-1980s antidepressants had several side effects due to their non-selective interference with neurotransmitters other than the serotonin target. The fluorinate floxidin was selective and one of the first to avoid this problem. Many current antidepressants receive this same treatment, including the selective serotonin reuptake inhibitors, citalopram, its enantiomer escitalopram, and fluvoxamine, and paroxetine. Quinolones are artificial broad-spectrum antibiotics that are often fluorinate to enhance their effects. These include ciprofloxacin and levofloxacin. Fluorine also finds use in steroids. Fludrocortisone is a blood pressure-raising mineralocorticoid, and triamcinolone and dexamethasone are strong glucocorticoids. The majority of inhaled anesthetics are heavily fluorinate. The prototype halothane is much more inert and potent than its contemporaries. Later compounds such as the fluorinate ethers sevoflurane and desflurane are better than halothane and are almost insoluble in blood, allowing faster waking times. A full-body 1/8F PET scan with glucose tagged with radioactive fluorine 18. The normal brain and kidneys take up enough glucose to be imaged. A malignant tumor is seen in the upper abdomen. Radioactive fluorine is seen in urine in the bladder. Fluorine 18 is often found in radioactive tracers for positron emission tomography, as its half-life of almost 2 hours is long enough to allow for its transport from production facilities to imaging centers. The most common tracer is fluorodeoxyglucose which, after intravenous injection, is taken up by glucose-requiring tissues such as the brain and most malignant tumors. Computer-assisted tomography can then be used for detailed imaging. Liquid fluorocarbons can hold large volumes of oxygen or carbon dioxide, more so than blood, and have attracted attention for their possible uses in artificial blood and in liquid breathing. Because fluorocarbons do not normally mix with water, they must be mixed into emulsions, small droplets of perfluorocarbon suspended in water, to be used as blood. One such product, oxacete, has been through initial clinical trials. These substances can aid endurance athletes and are banned from sports. One cyclist's near death in 1998 prompted an investigation into their abuse. Applications of pure perfluorocarbon liquid breathing, which uses pure perfluorocarbon liquid, not a water emulsion, include assisting burn victims and premature babies with deficient lungs. Partial and complete lung filling have been considered, though only the former has had any significant tests in humans. An Alliance Pharmaceuticals effort reached clinical trials but was abandoned because the results were not better than normal therapies. Fluorine is not essential for humans and other mammals, but small amounts are known to be beneficial for the strengthening of dental enamel, where the formation of fluorapatite makes the enamel more resistant to attack from acids produced by bacterial fermentation of sugars. Small amounts of fluorine may be beneficial for bone strength, but the latter has not been definitively established. Both the WHO and the Institute of Medicine of the U.S. National Academies publish recommended daily allowance, RDA, and upper tolerated intake of fluorine, which varies with age and gender. Natural organofluorines have been found in microorganisms and plants but not animals. The most common is fluorostate, which is used as a defense against herbivores by at least 40 plants in Africa, Australia, and Brazil. Other examples include terminally fluorine at fatty acids, fluorostone, and 2-fluorocitrate. An enzyme that binds fluorine to carbon, adenosyl fluoride synthase, was discovered in bacteria in 2002. Elemental fluorine is highly toxic to living organisms. Its effects in humans start at concentrations lower than hydrogen cyanide's 50 ppm and are similar to those of chlorine. Significant irritation of the eyes and respiratory system as well as liver and kidney damage occur above 25 ppm, which is the immediately dangerous to life and health value for fluorine. The eyes and nose are seriously damaged at 100 ppm, and inhalation of 1000 ppm fluorine will cause death in minutes, compared to 270 ppm for hydrogen cyanide. Regarding fluorine, and regarding hazards, here is the GHS labeling. It has pictograms. Its signal word is danger. Its hazard statements are H270, H314, and H330. It has a NFPA 704, fire diamond, of 043 WOX. Hydrofluoric acid burns may not be evident for a day, after which calcium treatments are less effective. Hydrofluoric acid is the weakest of the hydrohalic acids, having a pKa of 3.2 at 25 degrees Celsius. Pure hydrogen fluoride is a volatile liquid due to the presence of hydrogen bonding, while the other hydrogen halides are gases. It is able to attack glass, concrete, metals, and organic matter. Hydrofluoric acid is a contact poison with greater hazards than many strong acids like sulfuric acid. Even though it is weak, it remains neutral in aqueous solution and thus penetrates tissue faster, whether through inhalation, ingestion, or the skin, and at least 9 U.S. workers died in such accidents from 1984 to 1994. It reacts with calcium and magnesium in the blood, leading to hypocalcemia and possible death through cardiac arrhythmia. Insoluble calcium fluoride formation triggers strong pain and burns larger than 160 centimeters squared, 25 inches squared, can cause serious systemic toxicity. Exposure may not be evident for 8 hours for 50% HF, rising to 24 hours for lower concentrations, and a burn may initially be painless as hydrogen fluoride affects nerve function. If skin has been exposed to HF, damage can be reduced by rinsing it under a jet of water for 10 to 15 minutes and removing contaminated clothing. Calcium gluconate is often applied next, providing calcium ions to bind with fluoride. Skin burns can be treated with 2.5% calcium gluconate gel or special rinsing solutions. Hydrofluoric acid absorption requires further medical treatment. Calcium gluconate may be injected or administered intravenously. Using calcium chloride, a common laboratory reagent, in lieu of calcium gluconate is contraindicated, and may lead to severe complications. Excision or amputation of affected parts may be required. Soluble fluorides are moderately toxic. 5 to 10 G sodium fluoride, or 32 to 64 mg fluoride ions per kilogram of body mass, represents a lethal dose for adults. 1/5 of the lethal dose can cause adverse health effects, and chronic excess consumption may lead to skeletal fluorosis, which affects millions in Asia and Africa. Ingested fluoride forms hydrofluoric acid in the stomach, which is easily absorbed by the intestines, where it crosses cell membranes, binds with calcium and interferes with various enzymes, before urinary excretion. Exposure limits are determined by urine testing of the body's ability to clear fluoride ions. Historically, most cases of fluoride poisoning have been caused by accidental ingestion of insecticides containing inorganic fluorides. Most current calls to poison control centers for possible fluoride poisoning come from the ingestion of fluoride-containing toothpaste. Malfunctioning water fluoridation equipment is another cause. One incident in Alaska affected almost 300 people and killed one person. Dangers from toothpaste are aggravated for small children, and the Centers for Disease Control and Prevention recommends supervising children below 6 brushing their teeth so that they do not swallow toothpaste. One regional study examined a year of preteen fluoride poisoning reports totaling 87 cases, including 1 death from ingesting insecticide. Most had no symptoms, but about 30% had stomach pains. A larger study across the U.S. had similar findings. 80% of cases involved children under 6, and there were few serious cases. NASA projection of stratospheric ozone over North America without the Montreal Protocol. The Montreal Protocol, signed in 1987, set strict regulations on chlorofluorocarbons, CFCs, and bromofluorocarbons due to their ozone-damaging potential, ODP. The high stability which suited them to their original applications also meant that they were not decomposing until they reached higher altitudes, where liberated chlorine and bromine atoms attacked ozone molecules. Even with the ban, and early indications of its efficacy, predictions warned that several generations would pass before full recovery. With 1/10 the ODP of CFCs, hydrochlorofluorocarbons, HCFCs, are the current replacements, and are themselves scheduled for substitution by 2030 to 2040 by hydrofluorocarbons, HFCs, with no chlorine and 0 ODP. In 2007 this date was brought forward to 2020 for developed countries. The Environmental Protection Agency had already prohibited 1 HCFC's production and capped those of 2 others in 2003. Fluorocarbon gases are generally greenhouse gases with global warming potentials, GWPs, of about 100 to 10,000. Sulfur hexafluoride has a value of around 20,000. An outlier is HFO-1234YF, which is a new type of refrigerant called a hydrofluorolefin, HFO, and has attracted global demand due to its GWP of less than 1 compared to 1,430 for the current refrigerant standard HFC 134A. Perfluorooctane sulfonic acid, a key Scotchgard component until 2000. Organofluorines exhibit biop-resistance due to the strength of the carbon-fluorine bond. Perfluoroalkyl acids, PFAAs, which are sparingly water-soluble owing to their acidic functional groups, are noted persistent organic pollutants. Perfluorooctane sulfonic acid, PFOS, and perfluorooctanoic acid, PFOA, are most often researched. PFAs have been found in trace quantities worldwide from polar bears to humans, with PFOS and PFOA known to reside in breast milk and the blood of newborn babies. A 2013 review showed a slight correlation between groundwater and soil PFAA levels and human activity. There was no clear pattern of one chemical dominating, and higher amounts of PFOS were correlated to higher amounts of PFOA. In the body, PFAs bind to proteins such as serum albumin. They tend to concentrate within humans in the liver and blood before excretion through the kidneys. Dwell time in the body varies greatly by species, with half-lives of days in rodents, and years in humans.